Hello everyone and welcome to our second video of Module 3 on how we can use Zener diodes as voltage regulators. So in order to do that, we would like to start by having a simple example. So I'll just write here an example where we have a circuit that looks like this. Circuit has a voltage source, has a resistor, and it has a Zener diode. This is the very simple use of a Zener diode as a voltage regulator. Where we have our voltage here, V output, this is our input voltage, which we would like to see what will be the value of the input voltage that we can vary such that always our output voltage is a certain specified value. You will see that as an example, we would like to have Zener diode number 40 in our from our previous table. So I will just say here I have the Zener diode IN 4740A. So this is known as this specified diode that will be used. I have a resistor here of 220 ohms, and I would like to see how much voltage variation will be here such that I always have as my output voltage the value that is corresponding to this Zener diode. So if you notice and you go here and look at this 4740 diode, this is the diode here, or this is the one, and you can see if I just circle here to see what is the diode. This is my diode, and these are the information I care about. You can see that in this diode I have two very important currents that I have to start with. So the two important currents are the following. We do have a current, of course, mainly we are interested in the reverse biased region. So we know that here we will be having a current and we said, if you remember, that these currents are the following. So I have one current here and I have one current here, and we said that the first one will be IZK and this current will be IZM. These are the most important currents I have to take care of. Of course, this is our voltage and this is our current I, and this is a negative voltage. So if I look carefully for this Zener diode, I find out this is given to us, it's IZK. So IZK, which is the minimum current that will make sure that I have a reverse voltage characteristics of the Zener diode. I'll find it from here, and it's given to me as this current. So this is 0.25 milliamperes. So I have this number equals to 0.25 milliamperes. On the other hand, if I would like to get what is IZM, which is the maximum current, I can get it. Unfortunately, it's not given in the table here or in the data sheet, but we can calculate it from the numbers we just mentioned before. I can get IZM as my PD divided by what? Divided by VZ, which is the voltage of the Zener diode. So my Zener diode here is expected to keep the voltage equal to 10 volts. So this is over 10. And my power dissipation is 1, so that is 100 milliamperes. So I know here that this is equal, as we said, it's 1 over 10, which is 100 milliamperes. Now we know that if this is the case, then I can calculate what is the value of the voltage V here. The voltage V, or the voltage V here, is expected to be always 10 volts. This is what we said. But what should be the value here? I know that Vn is equal to VZ plus VR drop. So we have two cases now, if you remember. For the case of IZK, which is the minimum value, then V input will be what? 10 plus, what is the drop of the voltage? It's equal to 0.25 milliamperes multiplied by 220 ohms. And if you calculate this number, you will be able to get that this is just 10 point something. It could be like 10.055 volts. On the other hand, for the case of, so this is the minimum value of Vn. The maximum value of Vn will be when I have the maximum amount of current that's flowing here, and that will be again 10 plus 100 milli multiplied by 220, and if you calculate this number, it will be equal to 32 volts, because the voltage drop here by itself is equal to what? 22 volts. So this is 32, and as such I can say that this Zener diode can regulate an input voltage. Okay, it can, Zener diode can regulate the voltage from 10.055 volts up to 32 volts. So no matter what is the voltage, 10.5, 10.7, 11, 20, 25, up to 32, my output voltage here will be equal to 10 volts. That shows clearly how this Zener diode can operate in a very good manner. So we can continue by just trying to give some more cases where I would like to say that what if I have this circuit? I have a voltage supply, again, I have a resistor, and I have my Zener diode. And what if this Zener diode is, let's say, one of the ones that we have here. Let's say as an example, it was this number, which is 43. So this is 43A. But we know for 43A the voltage here is equal to 13 volts. It should be 13 volts. Okay. Now let's say that we have here as an example 1 kilo ohm, 1000 ohm resistor, and the voltage, I would like to see what will happen if I vary this voltage V input. So let's start by saying that my V input is equal to, and this is your V out. So ideally, if V input is equal to, let's say as an example, is equal to 5 volts, so what will be the voltage at this terminal here, which is V output? The voltage should be equal to 5 volts. Be careful, because simply this voltage, which is 5, is less than the breakdown voltage that we are looking to get for the case of Zener diode. We should have at least 13 volts in order to have a breakdown current and therefore breakdown the voltage. So if the voltage goes up to, let's say, 11 volts, I still have what? The 11 volts. So I should have the 11 volts here. If you increase to, let's say, 15 volts, then you'll be able to get what? The 13 volts. Of course, it could be 13.01 or 12.99, whatever. If you go to 40 volts, it will be the same, 13 volts and so on. But of course, we have to be careful what will be the maximum that will make it. And that depends, as we said before, on our value of V. So if I ask you, what will be the current that's flowing here? I will call it IR, which is equal to IZ. And we can calculate it from what? From the voltage drop between these two. So in this case, in the first case is here, IZ should be equal to what? 0, because simply this diode is not yet in the reversed the breakdown mode, and therefore there will be no current flowing. This is why we said that the voltage here will be the same as the applied voltage. So for this will be 0, for this will be 0. For this one, I will have 15 volts minus 13 volts divided by 1000. And if you see that this is 2 milliampere current, so this is 2 milliampere. The same thing here, you just say for this case, next one here, I will be having 40, so IZ is 40 minus 13, again divided by 1000, and this is what, 27 milliamperes here. Okay, so you have to be careful about this one, that current here in this circuit, it will only depend on the situation of the Zener diode. If the Zener diode is not in the reverse bias, or it's not in the breakdown mode, then the voltage will be the same voltage as the input 1. Okay, let's solve another example. And in this example, we do have the following circuit where we have a Zener diode. It has a voltage source, 10 volts. We have a resistor here given to us as 100 ohms. We have a Zener diode, and we have a load, and this load is called, let's say, RL, which is unknown, but we have a Zener diode that is with a VZ equal to 5 volts, and this resistance is 100 ohms. The question says, find the value, the minimum value of RL such that we maintain the output at 5 volts, knowing that IZK, which is the knee point of the Zener diode, is equal to 10 milliamperes. Also find the power rating, the minimum power rating of the diode, of the Zener diode. Now we got to be very careful in solving such a problem, because simply we know that this output voltage is going to be 5 volts all the time. So let's see how we can solve it. We will start by saying that, okay, let me redraw it again. So I'll be redrawing it here as an example, saying that this is what I have, plus minus, I have this resistor, I have this Zener diode, and I have this load called RL, and this is 100 ohms. Now the current can be designated as follows. I have current here, I will call it IS. Here I have I Zener, ZK, and here is I load. And I know that simply that IS is equal to I Zener plus I load. And we said that in the case of very good voltage regulation, the voltage here should be equal to 5 volts. This is 10 volts, and this should be 5 volts. So the voltage at A, and this is B. So under perfect voltage regulation, IS will be equal to 10 minus 5 divided by 100. And if we calculate this one, that will be equal to 5 over 100, or equals to, which is equal to 50, if you wish, milliamperes. Now, we know as well from given info that IZ or IZ is equal to 10 milliamperes. This implies that IL, which is the maximum value we can get, will be equal to what will be IS minus IGK or IG, which is equal to 50 milliamperes minus 10 milliamperes, which is equal to 40 milliamperes. So now we do have how much is the current that's flowing here, IL, and we know what will be the voltage across it. So in that case we can calculate what should be the minimum value of IL. So in this case that implies RL minimum, because I have the maximum value of the current. So that will be due to a minimum value of the resistance because the voltage is constant. So that will be the 5 volts, which is here, 5 volts divided by 40 milliampere. And if you calculate this number, that will be 125 ohms resistance. Now, in order to calculate what is the minimum, power rating for my Zener diode, I have to be very careful. Why is that? Because if I just say, okay, we know that the power generally in the Zener diode, it will be equal to VZ multiplied by IZK. Now, if I just use the numbers we have, that will be equal VZ, which is 5 volts, multiplied by the 10 times 10 to minus 3, which is 50 milliwatt. I just tried this answer. This is a wrong answer, because simply, who said that RL will be always with this number? It could be more. We said the minimum RL is this one in order to have voltage regulation. But if I have this number equal, instead of 125, what if I have it equal to 500 ohms? What if I have it 1 kilo ohm? I still have current flowing here. I still have the voltage the same, but more current will be here, because the current in this portion here would be the same. It's 10 minus 5 divided by 100, so that will be 50 milliamperes. If I have here only 5 milliamperes in this portion, then in that case I will be having the rest coming into the Zener diode. So I have to say that if RL is infinity, that implies no current will flow in RL. That implies my current IZK will be equal to the maximum value, which is equal to what? 15 minus 0, which is 50 milliampere. And in that case we can say that our power of the Zener diode will be equal to 50 milliamperes multiplied by the 45. That gives me 250 milliwatt. So this is the minimum. This is the minimum value of the Zener diode power. Now I would like to take another example. And in this example, I'd like to say that example. Say here. Say that was example 1 and this is example 2. Here, let's see, this is the example 1, and this is example 1, and this is example 2. So in example 2, let's say we have this circuit. The circuit shows that I have a voltage source that is varying, showing a minute, I have a Zener diode, and there is no load at all. But zener diode has VG equal to 7 volts, and this voltage is varying between 10 to 16 volts, and the resistance is 200 ohms. It is mentioned that the zener diode has an internal resistance. Zener diode has an internal resistance of, let's say, 10 ohms. So the question says, if the voltage V input varies from 7 or from 10 volts to 16 volts, what is the output voltage? Now this question can be solved by just first understanding that since the voltage here is greater than the zener voltage, this means that my zener diode is going to work in the breakdown region, and therefore, let's say, since V input is greater than Vg, and then the zener diode will operate in the breakdown region, and therefore I can have an equivalent circuit that looks like this. I have the voltage here and the resistor, and I can represent it by resistor and battery, and this battery is 7 volts, and this is 10 ohms, and this is the 200 ohms, and this is my V input. Now we can calculate our V output here by simply saying that the output voltage here is nothing but this voltage, but this voltage, so this voltage here, which we can say that this is the voltage here, it's nothing but the 7 volts plus current that will flow here, which is the same as this current, I will call it, multiplied by the sum of the 200 plus 110 times this I, this current times I, this current times 10 times I. Now how to calculate the current I? We will say, okay, for V input equals to 10 volts, that implies that I, let me say IS, I call it IS, is the same here or here, and IS I would call it 1, so VI equals to V1, I would call it V1 equals to 10, then IS1 is equal to what? It's equal to 10 minus 7 divided by 200 plus 10. This is from Kirchhoff voltage, and this is the loop. And therefore, if you calculate this number, that will be 3 over 200. And I will keep it like this. I will say in this case, I will say that, therefore, the voltage V output 1 will be equal to 7 plus 3 over 210 multiplied by 210 times 10. And therefore this would be what? This would be, okay, here, and this would be what? 210. So I will just take this with this, and then this will be 1 over 7, and this would be 7.14 volts. Now, let's take the case where we have V for V2 equals to 16 volts. What do we have in this case? We have IS2 equals to 16.7 divided by 200 plus 10. And that would be what? 9 over 210 amperes. Again, we have to do the same thing that we are 2 will be equal to 7 plus 9 over 200 and multiply by 10. And if we calculate this number, that will be 7.43 volts. So for such a case, I can tell that if the voltage input is between 10 and 16 volts, the output will be between 7 point, as you can see, between 7.14 and 7.43, which is a good regulation of my output voltage.